Hello class, welcome back to another Learning Glass lecture on physics. We're talking about electric fields today, and we touched a little bit on this last time, but let's review just a little bit. What's an electric field? So an electric field we write with a capital E, okay? And the electric field is defined as the force that a test particle would see divided by the charge of that test particle. What does that mean? Well, let's say we have a big positive charge right here. Okay. That positive charge is going to exert an influence on a test charge. If this happens to be a positive charge, then we know what's going to happen. Right? We talked about what happens to charges of the same sign. We said that likes repel. And so there is a force here, F, which is pushing that particle away. Right? Those two positive charges are going to separate. Okay, but let's say we don't have any charge there. Let's say we just erase it and we think about that region of space. And let's say that we are a distance, r, away from our charge, and that charge has a total value of q. What can we say about the electric field in this region? And what do we even mean by electric field? What we mean is, if I put a test particle there, would it experience a force? And if the answer is yes, then there is an electric field there. If the answer is no, then there's zero electric field there. All right, in this case, we know that it will experience a force. So there must be an electric field there, and the electric field is apparently F over Q naught. But we know what F is. F is Coulomb's law. So that becomes K Q naught divided by r squared. We're going to divide that whole thing by Q naught. And there is a particular direction associated with this. Okay? We typically call that r hat. What does r hat mean? That's out radially. So if you have a point charge sitting at the origin, this is our xy coordinate system. Remember, we talked about polar coordinates. R is along a radius, so r hat is a radial unit vector. It's pointing away from the origin in this case. It would be pointing away from the charge. Okay, we can cross out the Q naughts right away. And so this whole thing simplifies to the following: KQ over r squared r hat. And this is the electric field of a point charge. And this is a good thing to just burn into your memory. Electric field of a point charge, E, is KQ over r squared r hat. That r hat is just the direction. It means pointing away from the point charge. All right, so let's draw some electric fields. And just make sure we're all on the same page. If I have a positive charge, electric field lines go out from that positive charge. And if I draw it with continuous lines, like so, the arrows indicate the direction of the electric field. The lines indicate those lines of electric field. The density of those lines indicates the strength. Where the lines are tight together, electric field is strong. Where they are spread out, electric field is weak. Positive charges we call sources. Electric field lines come out from positive charges. Negative charges are called sinks. The lines look exactly the same, but what changes is the direction of the arrow. It's now pointing towards the negative charge, and those field lines end on the negative charge. Those we call sinks. So think about these words, sources and sinks, right? The source is like your faucet in your bathroom. You turn on the faucet, water comes out. The sink is where it drains into. It's where it disappears from your bathroom. Sources and sinks, positive and negative charges. All right, that's not too bad. When we put them together, we get the dipole field, and we talked about this a little bit earlier. And the dipole field looks like this. It goes out of the plus into the minus. And anywhere you draw those electric field lines, they had better come out of the plus. It becomes a continuous line, like so. You can draw one on the other side, and you can draw as many as you like. Okay, this is a dipole field. Lots of things in the universe are, of course, dipoles. And so this becomes an important field to be concerned about, the dipole field. Let's say we have a charge, positive charge sitting right there, and a positive charge sitting right there. And let's say these have values of capital Q. What is the electric field halfway in between? I'm asking you guys, what do you think? 0, right? We know that. It's 0. Why is it 0? Because the top charge is giving us an electric field that looks like that, pointing down. The bottom charge gives us an electric field like that, pointing up. If that point is halfway in between the two, they're equal and opposite. It cancels out. Everybody's happy. But let's make it a little more complicated now. Let's bring out our point to the side. So let's put our point of interest right there, and let's say that this distance is L, that distance is L, that distance is L, and let's calculate the electric field right there. How do we do it? Well, we know that we have an electric field from this one. It must be pointing in that direction. Let's call that E1. We know we have an electric field from this one that's pointing in that direction. Call that E2. Those are positive charges, so E field lines leave the positive charge. And if we want to calculate the net field at this point, how do we do it? E3 is just going to be the sum of those two, but they're vectors, right? We have to remember to put the little arrows on top. And now we have to be a little bit careful about determining what those vector components are. E1 is at some angle. It has some horizontal component and it has a vertical component. E2 is also at an angle, so it has some horizontal component and some vertical component. And if we call this angle theta, which means this is also angle theta, now we can determine what some of those components are. E1 is just going to be some x component, E1x, in the I hat direction. Remember, I hat is a unit vector along x. J hat would be a unit vector along y. So we're going to have some x component, I hat. There's going to be some y component along j hat. We need to figure out what those things are. Well, this E1 is a triangle. The hypotenuse is E1. The sides are E1x and E1y, and we said that is angle theta. So this just becomes E1 cosine of theta, I hat, that's this side of the triangle, minus, since it's pointing down, we have to put a minus sign right there, E1 sine theta, j hat. And now we can do the same thing for E2. E2 looks like this. It has an x component to it. It has a y component to it. This is angle theta. And so we can write down E2 very simply. It is going to be E2 cosine of theta, I hat, it's going to the right, plus E2 sine theta, j hat, it's going up. Now we have E1 and we have E2, and so we can add them up to get our resultant E. E3 is going to be what? Well, let's just look at this. I have E1 cosine theta, E2 cosine theta, but by symmetry, those have to have the exact same strength, right? Same charge, same distance, everything is symmetric, so E1 has to be equal to E2. E1 equals E2. And so we can rewrite this with ones here. And now when I add them up, look what happens. This one doubles, this one goes away. And so we get 2 E1 cosine theta I hat plus 0 j hat. It's all in the horizontal direction. And now we're nearly done. The only thing we need is the strength of E1 and that angle theta. So let's put that together now. So let's redraw the picture just for one of them. We've got a Q, and it was L on the top, L on the side. There's our point. That was our E1. Okay, and we need to calculate the strength of E1. Doesn't really matter if that was E1 or E2, since it's symmetric, it's going to have the same strength. What is the strength of E1? Well, we just learned that. It's the field of a point charge. KQ over R squared. Okay? That's the magnitude of E1. We've already taken into account the directions here with the I hats and the j hats. And so we just have KQ over R squared for the magnitude. Do we know R? Well, R is the hypotenuse of that triangle. That's a right angle. If that's a right triangle, then we know that R squared equals L squared plus L squared, which is just 2L squared. And so I can put that in right here. This is KQ over 2L squared. And now we're almost there. We just need one little piece of information, which is theta. Theta, we said, was this angle. But that angle is exactly the same as this angle. And since this side is L and that side is L, it's a 1, 1 square root of 2 triangle, which means theta is 45 degrees. And cosine of 45 degrees is 1 over root 2. And so now we have everything we need. E3, my 3 got a little funky. E3 is equal to 2 times E1, KQ over 2L squared, times the cosine of theta, 1 over root 2, and we have an I hat. Okay, and you can simplify that because the 2 goes away, and we get KQ divided by root 2L squared, all of that times I hat. That is our resultant field E3 due to those two charges. Questions about that? If you are confused about the unit vector stuff, the I hat, the J hat, the K hat, click to my YouTube channel and there is a whole lecture about unit vectors, okay, and it'll walk you through it. The idea is that I hat and J hat have unit magnitude, but they have direction associated with the x-axis for I and the y-axis for J. That's all it means. Are you pointing in the x or are you pointing in the y? Good, everybody okay with that? All right. Let's think again about the hydrogen atom for a second. This is one of our favorites because it's number 1 on the periodic table and all others are 2 or lower. So what does a hydrogen atom look like? Looks like this. Positive charge, negative charge, electron swirling around the proton at a speed v. And let's pretend that this is moving around at a constant speed, and so this is uniform circular motion, which we know and love. Later on, when you get to quantum, you're going to realize it's not really a point particle going around like a tennis ball on a string, but this is an okay model to start with. There is, of course, a force, F, that is holding it in that circle. That is Coulomb's force. And there is a distance, r, between the electron and the proton. So in a hydrogen atom, let's put in some numbers. R is about half an angstrom, 10 to the minus 10 meters. Let's calculate the acceleration of the electron. Okay, how do we do that? Well, this thing is moving in a circle. If you are moving in a circle, you have centripetal acceleration. We know that from last term, right? Anytime you're moving in a circle, you have centripetal acceleration. And it's not because your speed is changing, it's because the direction of your velocity is changing. Your velocity was this way, and then later on it's this way, and then so forth. If you're changing the direction of your velocity, that is an acceleration. But we know what acceleration is, and we know how it relates to force, right? Force is equal to ma, and we know what the force is in this case. It is Coulomb's law. So it is K Q1 Q2 over r squared. And now we can solve this thing for A. A is equal to K Q1 Q2 divided by mr squared. And now we have all those numbers. So let's plug them in. We've got a K, which is 8.99 times 10 to the 9. We've got a Q1, which is an electron. An electron has charge 1.6 times 10 to the minus 19 coulombs. There's another one that's a proton, but that also has the charge of the electron. And we need to put a minus sign out in front of the whole thing because one of those is negative. The electron is negative. And then we have the mass. It's the mass of the thing that's moving in the circle, so it's the mass of the electron. And you can look up the mass of the electron. It's 9.1 times 10 to the minus 31 kilograms. Remember, kilograms is SI units. And then we have 0.5 times 10 to the minus 10 is our distance, and we have to square that. Okay, and now you guys should pull out your calculator and plug in those numbers and tell me what you get, and we're going to approximate it here. So we have a 9 times 10 to the 9, and then we have 1.6 squared has got to be close to 3. 10 to the minus 19 squared is 10 to the minus 38. And then we're going to divide by 9 times 10 to the minus 31. And then we have 0.5 squared, which gets us a quarter. And 10 to the minus 10 squared becomes 10 to the minus 20. So if we punch all these in, what should we get? Well, 9's cancel out. 3 divided by a quarter is the same as 3 times 4. We're a little bit heavy, so let's lower it to not 12, but how about 10? And we've got a 10 to the 9 and a 10 to the minus 38. That's a 10 to the minus 29. And then down in the bottom, we have a 10 to the, I better write this down, 10 to the minus 29. That's still on the screen over there. Divided by, that is another 10, and so that becomes 10 to the minus 30, and then we have a 10 to the minus 50. 50. All right, good, and let's see what we get here. So we have a 10 times 10 to the minus 29, which becomes 10 to the minus 28, divided by a 10 to the minus 50, and so we end up with 10 to the 22. Is that right? Did we do that right? What'd you guys get on your calculator? Anybody plunge in the numbers? Yeah. Okay. Oh, that's right, because we had a 10 right there. I forgot that one. Okay. So you said negative 1 point what? 0 times 10 to the 23rd? Okay. That's right, and we had the negative sign hanging out in the front. Negative sign is just the direction. Good. 10 to the 23 meters per second squared, that is the acceleration. Specifically, it's the centripetal acceleration of the electron in its orbit, which is really high. That's a very big value, right? Gravity, how fast does gravity accelerate things downwards? 9.8 meters per second squared. This is 22 orders of magnitude bigger. That is a very big number. What about the speed? We said that the electron is orbiting at speed v. What is that orbital speed? Let's calculate it. So, Newton's law in circular motion. What did we have? We had the sum of the forces in the radial direction have to add up to mv squared over r. And those forces have to equal the mass times the acceleration, and therefore the acceleration, specifically centripetal acceleration, is v squared over r. We're talking about uniform circular motion. We're not accelerating the electron tangentially or slowing it down. And so we just have centripetal acceleration. We now have a number for that. This, we're only worried about the magnitude, not the direction. So we put in a positive number here, and we can solve this now for v. V is r AC square rooted. And we know r. We said r was a half an angstrom. 0.5 times 10 to the minus 10. Put some parentheses around that. AC, we just found, it's 10 to the 23. SI units, we'll take the square root, and that should do it. And if you punch that into your calculator, tell me what you get. It looks like it should be about 1 over root 2. And then we've got a 10 to the 13, but that's too hard to do. So if we make it this, a half times 10 to the 13, that's exactly the same as 5 times 10 to the 14. And square root of 10 to the 14 is 10 to the 7. Square root of 5, I'm sorry, this should be 12, right? Good. Should be 12. Square root of 10 to the 12 is 10 to the 6. Square root of 5 is a little bit bigger than 2, right? So I'm going to say this is about 2.3 times 10 to the 6. And did anybody punch it into your calculator? Okay, so this should be a 2.2. So we were close. 2.2 times 10 to the 6 meters per second. Okay, which is cruising, right? Electron is really, really moving very fast in that hydrogen atom. Why? Because it's very close to the proton. There's a really strong force on it. And so to keep in its orbit, it has to be moving really fast. We remember that from gravitation. When the space shuttle is in a low orbit, it's moving very fast. If it goes up to a higher orbit, it moves slower. So electrons that are near the nucleus have to move very fast. When they get further away, they can move quite a bit slower. Okay? That's a pretty fast number, right? Speed of light is 3 times 10 to the 8th meters per second. So this is like 1/100th the speed of light. Those things are moving. Let's talk about one of your homework problems. Okay, and the homework problem says the following. You're going to walk across the carpet. Here's the carpet. And when you walk across the carpet, you pick up charge. And now you have a net charge on you. And we talked about this in class. When you walk across the carpet, what kind of charge do you pick up? Do you pick up protons or do you pick up electrons? You pick up electrons. Electrons are hanging out on the tips of the carpet and they jump from the carpet to your shoes the same way that the electrons on your hair jump from your hair to the balloon when you rub the balloon on your head. You charge up the balloon with electrons. So you have a net negative charge. You are negatively charged when you walk across the carpet. Okay. Let's figure out how many electrons you actually picked up. And let's say that you acquired a charge of the following. 50 microcoulombs. 50 microcoulombs. That's probably a reasonable number for walking across the carpet. How many electrons is that? All right. We're just trying to convert from one unit to another. The unit that we're in is microcoulombs. The unit that we want to get to is electrons. Electrons, of course, have charge. We need to figure out what that conversion is. Let's start with the easy one, though. 50 microcoulombs is equal to 50 times 10 to the minus 6. That's what a micro means. Right? Micro is a millionth, which is 10 to the minus 6. And now I want to multiply this by 1. Anytime you're converting units, you just want to multiply by 1. And you look at the units that you need to cancel. You need to cancel coulombs, so we had better put coulombs down in the bottom. We want to get electrons, so let's put electrons up in the top. And what do we know? Well, 1 electron has how much charge in coulombs? 1.6 times 10 to the minus 19. So this is really the number 1. It's in some funky units. but it's the number 1. 1 electron equals 1.6 times 10 to the minus 19 coulombs. That's it. And now we just have numbers to multiply. The units here cancel. And we get 50 times 10 to the minus 6 divided by 1.6 times 10 to the minus 19. And we're left with electrons. And now you can run this number in your calculator. I'll approximate it here. 50 over 1.6, that's the same as 5 times 10 to the minus 7, or sorry, 5, right? 5 times 10 to the minus 5 divided by 1.6 times 10 to the minus 19. And 5 over 1.6, it's got to be really close to 3, right? Maybe a little bit more, 3.1 times 10 to the what? We've got a minus 5 up there. We have a minus 19, so we're going to add 19 to a negative 5, and so we get 14. And did anybody punch it into their calculator? What'd you get? Same thing? Okay, good. Same thing. Okay. This is the beauty of doing math in your head, and also the beauty of doing the lecture twice. All right. So we've got 3.1 times 10 to the 14, and this is a number of electrons. That's how many electrons you pick up. And these, we said, were probably realistic numbers. So that's sort of amazing, right? This is 310 trillion electrons that you pick up just walking across the carpet. So there's little fibers with tons of those electrons just ready to jump off and land on you. Okay, any questions about that one? There's a second part to it, which is how much mass does that correspond to, and you can do that conversion yourself. All you need to know is the mass of the electron, which we know is 9.1 times 10 to the minus 31 kilograms. One thing that we need to talk about is electric fields in metals. Okay, we mentioned this earlier in class, but let's refresh our memory. The idea is this: electrons in metals are free to move. This is what makes it a metal. Later on, we're going to learn about resistance, and resistance has to do with trying to not let them move so easily. So all conductors have a resistance associated with them, unless it's a superconductor. Okay, then the resistance goes to 0. But for now, let's not worry about any resistance. Let's just pretend those electrons are basically free to move. So here is a material, gold, which is a metal. And if I put an electric field on it everywhere, then charge in the metal starts to move. The protons don't move, okay? The electrons are the ones that move. So the electrons that were on these atoms in the center suddenly start moving to the left until they pile up on the left side. And they do this very quickly, okay, on the order of picoseconds. The positive charges that are left over here are missing an electron. You got a nucleus there, and one of its electrons migrated away, and so it's a net positive charge. And so now you have positive charge on the right, negative charge on the left, and that means there has to be an internal field that looks like this. Okay, there is some field that develops in the material. But remember, E is everywhere. Okay, E is not only outside, it's inside the material. And so when we calculate the net E in there, we have to worry about not only the internal field, but that external field. And those are pointed in opposite directions. Okay? And so if we just worry about the magnitudes at this point, we can write it like this. And that's going to be 0. The E field in here is 0. You know it has to be 0. Why? Because if it wasn't, then charge would still be moving. So once the charge separates and we have the static case, which is you've reached equilibrium, then there's no more electric field in there. Because if there was, charge would still move. Okay, and so we have rules for conductors. We have 5 separate rules that describe conductors in the static case. And I want you to make sure that you understand that this is the static condition, because later on we're going to talk about things that are actually moving. Charge is still moving. So the first rule is just what we said. E equals 0 inside. If you are inside the metal, the electric field is 0. Good. The second is any excess charge has to be on the surface. So we saw that all the negative charge went over to this side, and all the positive charge stayed over on this side. If you sprinkled some more charge on there, it would all go to the surface. Okay? Any excess charge that you put on a conductor goes to the surface. It doesn't have to be in an external electric field or not. If you took a ball, a metal ball, and you just sprinkled some electrons on it, which we know how to do now, right? You take a metal ball and you drag it across the carpet. That's going to put electrons on it. They immediately go to the surface. And in fact, in the case of a sphere, all those electrons will distribute themselves uniformly. Okay? They'll all go to the surface. If it's a thin rod, it's a little more interesting. If I have a thin metal rod and I drag it across the carpet, and then I ask you, where are the electrons on that rod? They are no longer uniformly distributed. They are bunched up around the ends. Okay? They are bunched near the ends. And this is one of the reasons that carpet fibers tend to have a lot of electrons on the end of the carpet fiber. It's pushing all those electrons out to either end. So it's kind of weird, but thin rods have more electrons on the ends than they have in the middle. All right, there's also no net charge inside. So in the volume of the material, every positive charge has a negative charge right next to it. Those atoms in there are neutral. It's the same voltage everywhere. We're going to learn about voltage tomorrow and the next day. But the idea is that voltage relates to electric field. We'll see how it relates. And you're familiar with voltage, right? If I have a battery, that has 1.5 volts. If I connect wires to the battery and I look at the ends of those wires, that voltage is still 1.5 volts. And it's because the voltage in that metal, in that conductor, is the same everywhere. And the last is that the electric field is perpendicular to the surface. This is external electric field. So if you have an object that has some complicated shape, this is a metal, and you did have some charge on it, it would make an electric field that is everywhere perpendicular to its local surface. Maybe that one doesn't look very perpendicular. Let's change it. There we go. Okay, these are the 5 rules for conductors. If you just start with E equals 0, everything else falls out of that. Okay? All the other rules follow from E equals 0.
I have a question.
Yeah, Sam.
So for the distribution of the electrons between the sphere and the thin rod, does it depend on the shape or on the type of material?
It depends on the shape.
On the shape.
Yeah. So basically, the shape is important because the charges are trying to redistribute themselves such that the electric field is 0 inside. Okay? And it makes sense that if I had a thin rod, it couldn't just be distributed like that uniformly, because if I was looking at a point right here, I've got 1 charge on my right, I've got 4 on my left. That would lead to an electric field, right? So that can't be right. And it turns out to be a really exquisitely hard physics problem to determine the distribution of charge in a thin rod. It's very challenging, very difficult, okay? Well beyond what we're talking about in this course. But this simple example tells you it can't be uniformly distributed, because that would make E point to the left. And if E is pointing to the left, then this electron is going to move to the right. But I can make the same argument over here, and so this one would move to the left, and what you end up with is a very complicated distribution. It's bunched up around the ends, and then less in the middle. Yeah. And this is a problem where we have to find the net electric field midway between 2 charges. Okay, and let's give you some numbers here and a picture. This is charge Q1. This is charge Q2. We are a distance midway between, and we'll call the total distance L. And let's give you some numbers here. So Q1 is going to be 5 microcoulombs. Q2 is -3 microcoulombs. And L is equal to 6 centimeters. Okay, and we want to find the E field right in the center, right there, midway between. Okay, how do we do this? Well, E fields are vectors, and we can use the principle of superposition to figure out what the E field is right here. And the E field is going to consist of 2 E fields, E1 and E2. And so all we have to do is figure out what the E field is due to Q1, what the E field is due to Q2, make sure we get the directions right, and add them up. So let's do 2 different problems. We'll do Q1, and we know that Q1 is a positive charge, and our point is sitting right there, a distance L over 2 away from Q1. Q1's positive charge. Is the E field here pointing to the left or to the right? Is it pointing towards the positive charge or away from the positive charge?
Away.
Away. Okay, E1 is pointing to the right. Perfect. We also know the strength of the E field, right? Because E field is KQ over R squared from a point charge, and so it just becomes KQ1 divided by r squared, but r is how far are you from the point charge. And so that becomes L over 2 quantity squared. And that is pointing to the right, and so we need to give a direction to it. I hat. We'll call this the x direction. So to the right is positive. That's an I hat. All right, what about the E field due to Q2? Q2 is sitting right there. Our point of interest is now to the left of it, a distance L over 2 away. And we said that Q2 was negative, right? Q2 is a negative charge, so we put a little negative sign right there. If that's a negative charge, what direction is the E field at this point? Is it away from the charge or towards the charge? Towards the charge, right? Negative charges are sinks. So E2 is pointing towards the negative charge. And now we know exactly what E2 is. E2 is K Q2 over R squared. And we know what R is. We'll just put that in right now. L over 2 quantity squared. And we know that it's to the right. And if it's to the right, then we can put an I hat right there, as long as we remember that this Q2, we're going to use a positive number there. You've already taken into account the direction with this arrow. So you don't want to put an extra negative in there, because that would flip that arrow back to the left. Okay, so this is what we want for E2. Okay, so here we go. We've got charge Q1 gives us a field E1. We've got charge Q2 gives us a field E2. They're in the same direction, so we want to add them up. E is just E1 plus E2. Definitely going to need some new pens in here. We'll try the pink one. Okay, and now we know what those are. E1 is K Q1 divided by L over 2 quantity squared. That is in the I hat direction. E2 is K times the magnitude of Q2 divided by L over 2 quantity squared. Both of those are in the same direction, I hat. And now we have some nice common factors here. We have K in both of those. We have L over 2 quantity squared in both of them. And then we have Q1 plus magnitude of Q2, I hat. Okay, and now let's put in those numbers and see what we get. What did we have for, well, K is 8.99 times 10 to the 9. What did we have for L? 6 centimeters. So in SI units, that's 0.06. We're going to divide that by 2, and then we're going to square the whole thing. Q1 was 5 microcoulombs, is that right?
Yeah.
Okay. 5 times 10 to the minus 6. And Q2 was -3. So since we're doing the magnitude, it's going to be positive 3 times 10 to the minus 6. And then all of that is still multiplying I hat. And now, why don't you guys plug this in to your calculators and tell me what you get. I will approximate it here. Okay, which is a good exercise. You should go through this yourself because it's good to have these skills. So that's a 9 times 10 to the 9. We're going to multiply by 8 times 10 to the minus 6. And then we're going to divide by 0.03 squared, which is 3 times 10 to the minus 2 quantity squared. All right. 9 times 8 is 72. We have a 10 to the 9 and a 10 to the minus 6, so that's a 10 to the 3. Downstairs we have 3 squared, which is 9. 10 to the minus 2 squared is 10 to the minus 4. So 72 over 9, we just went backwards. It's 8 times 10 to the 7 in the I hat direction. So that's my guess. What did you guys get? That's the answer? Okay, good. 8 times 10 to the 7. And so the strength of the electric field is the number out in front. 8 times 10 to the 7. And the SI units are volts per meter. And the direction is I hat, which in our picture is towards the negative charge. Towards the minus charge. Okay, that's the direction. Okay, good one. Any questions about that? Not too bad? Okay. Don't get too wrapped up with the signs. Always go back to your picture for the vectors. That'll tell you if you should be adding them or you should be subtracting them. Okay, go back to your picture of the vectors themselves. Okay, let's talk about Gauss's law. This is one of the biggies and one of the more difficult concepts to understand. Gauss's law is an approach to calculating electric fields for different charge distributions. And if you keep going on in physics, you're going to get to a very complicated form of Gauss's law. Okay? And just for fun, let me show you what it looks like. That's what it looks like. Del dot E equals rho over epsilon naught. Okay? This says the divergence of the E field is equal to the charge density rho divided by epsilon naught. You can also write this in integral form. Integral of E dot dA equals Q enclosed over epsilon naught. That is a closed surface integral of E. It's equal to how much charge is enclosed divided by epsilon naught. So some of that stuff looks completely foreign to you, but some of it looks familiar, right? There's an E. Oh, we know what that is. There's a Q. I know what that is. Epsilon naught, we heard about that. That's permittivity. This integral stuff maybe is a little complicated, but it's really not that bad. This simplifies greatly in a lot of cases to the following. EA equals Q over epsilon naught. And that's what we talked about today in class. Okay? Know that there is a lot more to it, but it simplifies in a great number of problems to just this. E times A equals Q over epsilon naught. So let's attack it from that point of view. Okay, let's talk about Gauss's law. This is one of the biggies and one of the more difficult concepts to understand. Gauss's law is an approach to calculating electric fields for different charge distributions. And if you keep going on in physics, you're going to get to a very complicated form of Gauss's law. Okay? And just for fun, let me show you what it looks like. That's what it looks like. del dot E equals rho over epsilon naught. Okay? This says the divergence of the E field is equal to the charge density rho divided by epsilon naught. You can also write this in integral form. Integral of E dot dA equals Q enclosed over epsilon naught. That is a closed surface integral of E. It's equal to how much charge is enclosed divided by epsilon naught. So some of that stuff looks completely foreign to you, but some of it looks familiar, right? There's an E. Oh, we know what that is. There's a Q. I know what that is. Epsilon naught, we heard about that. That's permittivity. This integral stuff maybe is a little complicated, but it's really not that bad. This simplifies greatly in a lot of cases to the following. EA equals Q over epsilon naught. And that's what we talked about today in class. Okay? Know that there is a lot more to it, but it simplifies in a great number of problems to just this. E times A equals Q over epsilon naught. So let's attack it from that point of view. You can immediately forget what I just said. Let's say we have the following. Let's say I have a positive charge Q, and we're going to draw some field lines. All right, we know how to do that. Field lines leave positive charges. This is the electric field E. But now let's double the Q, plus 2Q. And so we've got this, this, and so forth. We're going to get 8 lines instead of 4 lines. Okay, we had 4 lines here. Now we have 8 lines. And you can see what's happening, right? When I double the charge, I double the field lines. And this is really the whole point of Gauss's law if we do one more step. And that's, let's draw some spheres around these things. So here's my plus 2Q. I'm going to put a spherical shell all the way around. Hopefully you can see that okay. And that shell is called a Gaussian surface. In this case, it's a spherical shell. So think like a basketball, right? Just the outside edge of a basketball. Well, let's see if we can figure out what's happening inside. What we said was 2Q is going to give us 8 field lines. So I'm drawing them with dashes because they're inside the sphere. But eventually, they're going to poke right on out. And here they come out of the sphere. Okay, 8 field lines are coming out of this sphere. If I drew it with 1Q in there, then 4 field lines would be popping out. And so this is Gauss's law. The field lines through the surface is proportional to the charge inside. That is it in words. We just wrote it down mathematically. This is what it says in words. I've got 2Q, so 8 lines came out. If I had 1Q, then 4 lines would come out. It's proportional to the charge inside. This right here is called the flux. What's the flux? How many field lines are coming out of the surface? This is proportional, right? That's what that little alpha means. It means proportional. That's, of course, our charge Q. All right. But electric field lines is not flux. If I multiply it by the area of the surface, there's some area A of that surface, that is flux. Okay? That is flux, and that is equal to Q over epsilon naught, where epsilon naught is our proportionality constant. It's proportional to Q over epsilon naught. Epsilon naught is called the permittivity of free space. It has a value in SI units of 8.85 times 10 to the minus 12, and you can put the units on there. It's some funky units. So when you are asked the question, what is the flux, this thing is what you want. The flux is E times A. All right, so let's take a look at one of your homework problems that, in fact, deals with that question. So let's say we have the following. We have 3 objects. O1 has a charge of 5 microcoulombs. O2 has a charge of minus 6 microcoulombs. Object 3 has a charge of 0. And let's put those 3 objects right here. Here's object 1, here's object 2, and here's object 3. And let's ask a few different questions. Let's ask, what is the flux through area 1? Let's ask, what is the flux through area 2? And then let's ask a follow-up question, what is the flux through area 3? Okay, so we have a big sort of peanut. We have a sphere here for A2, we have a sphere here for A3. And we want to find the flux through area 1, area 2, and area 3. All right, flux we usually write with a capital Phi. I don't know if he does in your textbook or not, but typically you write it with a capital Phi. That is just E times the area, and Gauss's law tells us it's Q over epsilon naught. This is enclosed in that surface, enclosed in the Gaussian, let's be clear, Gaussian surface. Okay, what is inside that closed surface? Okay, so area 1, phi 1 is just going to be how much charge is there inside area 1 divided by epsilon naught. Area 1 covers everything. So that's going to be the charge of object 1, 5 microcoulombs, plus the charge of object 2, minus 6 microcoulombs, plus the charge of object 3, which we said was 0. All of that over epsilon naught. And so you get minus 1 microcoulomb, which is times 10 to the minus 6 coulombs, divided by epsilon naught, which we said was 8.85 times 10 to the minus 12. And you can put on the units there if you want. And so what do we get? I don't know, somebody run that in your calculator and tell me what you get. It's about 1 over 9, a little bit more. 1 over 9 would be 0.11, but it'd probably be more like 0.12. And then this is going to be 10 to the minus 6. I have to add 12, so I get a 10 to the 6. So I'm going to say this is minus 1.2 times 10 to the 5, right? I moved it over 1, and so we need to drop 1 from there. Is that what you guys got in your calculator? Did you try that? 1.1. 1.1? Okay, so 1.1 in the calculator times 10 to the 5, and you can figure out what the units are on that. Okay, it's going to be E times A, and so the units we said for E are newtons per coulomb, and A is square meters, so it's going to be Newton meter squared per coulomb. Okay, that's flux phi1 through the whole thing. Let's think about flux phi2 through A2. Phi2 is going to be the Q enclosed in its shell divided by epsilon naught. How much Q is enclosed in A2? It's only O3, but O3 has 0 charge on it. So this is 0 over epsilon naught, and so that is 0. There's no flux coming out of this one. What about phi3? Phi3 is also Q over epsilon naught. How much charge is enclosed in A3? Is there any charge in there? No, there's 0. 0 charge enclosed in A3, so that one is also 0. Let's talk about that for a second. And let's ignore some of these other areas. Let's just worry about A3. A3 is sitting right there. Let's draw it a little bit bigger. And let's draw O1, which we said was a positive charge, O2, which we said was a negative charge, and here is our area, A3. I have a positive charge sitting right here. Are there electric field lines coming out of that positive charge? Absolutely, right? We know what it's doing. They're pointing radially out from the charge, like so. A few of those are pointing right at A3. And so this field line doesn't just stop, it's going to keep going, and then it goes into A3, but then it comes back out of A3. And we don't have to draw that one. Let's think about the negative charge. The negative charge also has field lines, but it's coming in to the negative charge. But this line came in from much further out, so it had also gone through A3. But what is flux? Flux is field lines in minus field lines out. How many field lines are going in minus how many field lines are going out? Actually, it's the other way, I think, is the way we typically define it. So we'll change this to field lines out minus field lines in. And that way it's a positive number if there's a positive charge in there. So how many field lines are going out? Well, I've got one going out there. I have another going out there. So that's 2 going out. But I have 2 field lines going in. That one came in there. This one came in right here. And so this becomes 2 minus 2, which is, of course, 0. And so we're back to this idea that it only depends on the charge enclosed. How much charge is enclosed in your Gaussian surface? That determines how much flux is coming out of your Gaussian surface. Now, the entire point of Gauss's law is to find E. It's to help you use mathematical tricks to find the value of E. That's all you're trying to do with it. You're not really interested in the flux eventually. You're interested in E. And Gauss's law helps you find that. All right. Questions about that? Everybody fully saturated? All right. All right, why don't we wrap for today, and I will see you guys tomorrow online and Thursday face-to-face. Have a great day. Cheers.